So we're Smart Home Device 1. We're all about working hard, working smart, not hard. I'm Gilberto Lee. I'm a third-year double major in mechanical and material science. I'm the project lead. This is Alan. He's a fourth-year mechanical engineer. Glenn Shaw, fourth-year applied physics major with a concentration in electrical engineering. And our fourth member, Arnaldo Sanchez, is a fourth-year mechanical engineering major. So, Alan.
I'm going to give you guys a little background on the project. So this project started because we were all interested in smart home devices, and we did some research and we found out that smart home device sales are on the rise. In 2018, there were 90 million smart home devices sold, and that number is projected to increase to 120 million by next year. And at first, we weren't sure what smart home device we wanted to create, but one of our team members, they had an idea because their grandma, she had trouble opening and closing her blinds because she's at an old age. So we thought, why not try to make an automated shades device to help her out. And after some more research, we found out that only 5% of households that own smart home devices own smart shades. So there's a potential to tap into a market that's expanding. And existing automated shades already exist on the market, but they have much room for improvement. Many of them have inefficient designs that lead to motors overloading, and they also have difficulty controlling the shades. So some of the key components of this project are the mechanical, electrical, and controls part of it.
Yeah, just to go like a little more in depth, what we're doing is we're building a system that would retrofit existing shade systems that are driven by chains or cords, and we're building a system that you can control using the Google Home Assistant. So the requirements for this.
Okay, so some requirements for this product are, it has to be able to articulate movement of a shade system for a household window up to 16 feet squared of shades. In addition, it has to fully extend and contract within 15 seconds of command. The gear also has to, the gear that controls the system has to function with various shade systems, like Gilberto said, with chains or cords. And the device should be able to mount to walls or ledges. They should also only occupy one power outlet. And the device should be able to be hardwired into the house using proper connections. And it has to be easily connected to a Google Home ecosystem with a 5 to 10 minute setup.
Cool. So our goal is, by the end of the spring quarter, to create a working prototype of this device, which raises and lowers the shade versus voice commands to the Google Home Assistant. So for the mechanical objectives.
For mechanical, we have to design and build a model window frame in which we can attach the device. We also have to design and 3D print a versatile motor chain interface. And the last objective is to design and fabricate housing for the mechanical, for the motors and the electronics.
For our electrical objectives, first we have to choose the components that we want to use in our system because we have to make sure all of them are compatible. And after that, we have to design a power delivery system to make sure that all components are powered properly and not overheating or receiving too much current or things like that. And then after we verify that the power delivery system is correctly outputting the correct voltage to all the components, we want to make it more compact, make it more efficient so that there's not like a lot of wires around and no connections will fall out accidentally. And later on, we want to design a custom printed circuit board to really minimize this and be able to put the entire power delivery system into the product itself.
Yeah, so as far as computer science goes, none of us are computer science majors, so our first task is learning relevant coding languages. That includes Python, Arduino, HTML, and some JavaScript. Maybe a couple other languages depending on what we see fit. So we also have to flash the microcontroller with either Arduino or MicroPython, which are like firmwares to deal with programming the microcontroller. So, and a microcontroller is kind of like the brain of the device. We have to read and write to a cloud-based database for device state information. You know, if we want to check whether it's up or down already, and if we want to alter that state. We have to access or implement the voice control via Google Home Assistant also. So that's like dealing with the Google API, etc. So as far as organization, I'm the team lead. I'm in charge of team logistics and control systems. So like scheduling meetings, keeping everyone on track, etc. And then programming the microcontroller and writing any code for the cloud-based applications that we're using. Alan is in charge of documentation mostly, and working with Arnaldo on mechanical designs. So he does like some CAD and stuff like that with Arnold. Arnaldo is in charge of mechanical design and applications, so he takes lead on all the CAD and designs, and then he's also working on optimizing and 3D printing. We have access to a 3D printer, CR10S5, which is a pretty large 3D printer that he's working on optimizing. And then Glenn is in charge of electrical engineering, which means like power delivery system, hardware, etc. And then eventually he'll also design the printed circuit board. And then our advisor is Dr. Daniel Arlum from the Materials Science Department. So as far as our timeline goes, we're shooting for finishing this project before the start of spring quarter. So these are our document timelines, our review timelines, and then our milestones. For our milestones, coming up fairly soon is to design and wire a system to power the microcontroller, ESP32 at 3.3 volts, the LM298N, which is a motor controller that runs at 5 volts, and then a 12-volt stepper motor. Next up is we're designing, we want to have the mechanical and electrical portions designed by the 25th of January, which is kind of here early winter quarter. So we can start like testing, making sure it works. And then by a couple weeks later, we want to be able to control our client device, which is like the shade system via voice commands through Google Home Assistant. So hopefully we'll have our code by then, and then in these last few weeks of the quarter, we'll work on kind of like polishing it up, getting it ready for presentation. So having a presentable first prototype, all electronics properly soldered, insulated, and housed, the mock window frame, the shade system installed, and the prototype attached and ready to go.
To go over our budget, our total budget estimated is about $1,000, and that includes mechanical, electrical, computer science, and a safety budget, of course. So for the mechanical part, we budgeted $550. The bulk of this is using the 3D printer and using the third-party part fabrication, because we won't be making a circuit board ourselves. We also delegated some money to shade, which we're using to build a prototype, and wood, which we're using to build a mock frame for the shade. We also need filament for the 3D printer, as well as fasteners for putting the entire frame together. So for computer science, we have a little bit of money for the website domain, and then some books and other materials that we have paid for to learn computer science. For the electrical portion, this is where a lot of like small components are being purchased. So we have resistors, we have the motor, we have the L298N motor driver, we have the ESP32, which is like a stronger version of Arduino. We have the jumper wires, which are used to connect all of these. We have a switch for turning the device on and off. We have LEDs to make sure that everything is powered correctly. And we have things like a breadboard, a power supply unit, and a wire stripper for connecting the wires together. So for the electrical engineering progress, the first step was to make sure that we purchased components which were all compatible with each other. This included a lot of online research, looking at specification sheets, mostly through Amazon, so that we could get the parts delivered immediately and start working on this really quickly. After this, we needed to, I collaborated with Alan and Arnold to see like what mechanical products that they wanted to purchase, and make sure that the motor that I chose was able to actually lift the shade that they chose based on the torque strength of the motor and the weight of the shade per meter. So then I needed to engineer a power delivery system, which was pretty much the biggest step in this process. And fortunately, we wanted this product to be able to be powered from any outlet in California. And so I had to do research on what kind of voltages and what kind of signal comes from the outlets in California. And then figure out a way to tone down that voltage to be able to power a system because the voltage is very high. And so on the right side of this slide, you can see an image of a circuit that I designed in Circuit Lab, which includes a bridge rectifier, which turns an AC signal into a DC signal because our outlets output 120 volts AC signal at 60 hertz. After that, it turns into a DC signal. It goes through a voltage divider, which lowers the voltage, and so that it's actually safe for us to use with our device. However, I checked this. I sent this to one of my old electrical engineering TAs and checked with him to see if this was actually a plausible solution. And he said, well, theoretically, like all of this is correct. It's still a very dangerous task to do if you don't have the correct industry like Schottky diodes. So he suggested that I use a different laptop power supply or a computer power supply unit to build my power delivery system. So what ended up happening was I decided to turn a computer ATX power supply unit into a bench power supply unit. And an ATX power supply unit can output 3.3 volts, 5 volts, 12 volts, and negative 12 volts, which is enough because the highest voltage we need is 12 volts for our motor. And so this process included taking an ATX and taking the 20-pin ATX cable and then connecting it to a lot of resistors. I needed several power resistors to be able to mimic a dummy load because one of the safety mechanisms of a power supply unit is that it won't turn on if it doesn't think that it's connected to a motherboard. So I needed to build a circuit using resistors to simulate that it was connected to a motherboard because we are actually going to have it connected to a computer in the process. After that, it was also connected to several LEDs to make sure that the power is being outputted correctly, and we were able to successfully measure the voltages from all the pins. And this is just a diagram of the dummy load that I engineered and designed also on Circuit Lab, as well as a switch on the right side for turning the device on and off. And the next step of this is to just solder all the components together to make sure that nothing falls out.
So the mechanical portions that we have completed so far are we designed a gear to specifically work with the Vita chain to control the system. And we need to design a new compartment to fit gears and motors. Our original design was on the bottom, and that operated on a spool system, but we didn't like that idea because it would force the user to replace their old existing system with a new, completely different system. So we rather create a chain motor interface in order for it to be more retrofit and fit existing systems. We also designed and built a model window frame to attach our device onto, and the inside dimensions of it are 3 feet by 2 feet. And the last step that we need to accomplish, we need to finish designing the motor chain interface.
Cool. So as far as the computer science goes, we built a globally accessible server using one of our ESP32s. It's running Arduino firmware. So basically, we're using a residential IP address, port forwarding it. That's basically like when outside websites and devices contact our website, it drives to one of our home networks, and then our home network redirects it to our ESP32. One problem we encountered with this is that ISPs, internet service providers, they block some of the port redirects. So they're listed here. So the workaround was we used port 8080 to redirect that connection. Another thing we had to look into was that with a private like home IP address, internet service providers are constantly changing your IP address based on like what's available and whatnot. So we needed a dynamic update client to deal with updating our dynamic domain name system, or DDNS. So essentially, we implemented that using one of the computers that we had on hand. But moving forward, we decided...
Sorry, you'll have to just let people read it.
Okay.
Do you have any more slides?
We have just kind of proved the concept.
Okay. Time is up, though, so if you want to say a 30-second wrap-up.
Okay, just real quick, I guess we started coding here's some of our code. These are like the libraries we're using. This is what our server looked like. We're no longer going with this server because it's kind of outside the scope of our needs. We're just going to use cloud-based databases in the future and work mostly on the client side, which is the device that connects. So right here, you can see we're reading the spreadsheet. But yeah, I'll wrap it up there.
Okay. All right. Good.